Other type of corrosion typical in oil and gas is the erosion corrosion. Erosion corrosion is the cumulative damage induced by electrochemical corrosion reaction and mechanical effect from relative motion between the electrolyte and the corrosion surface. It could be impingement or cavitation, the ones that cause erosion corrosion. In this example, we see this is a 6-inch pipeline, 6-inch diameter, and it's tied a 3-inch pipe inside there as a lateral. So the flow in the 3-inch, just because it's small, it's larger than the flow in the 4-inch. So this is much more flow in this direction and less flow in that direction. And it is how it looks. So at the how it's basically tied, this is the weld, and it seems all this some sort of erosion problem there causing the damage in this. So it's exactly where it ties. It ties there when it welds. Basically, we see the weld, and then it's how is the flow basically damaging that area. When we have erosion corrosion problems, the protective scales or the passive layers could be compromised, even the films. So if there is a compromise on the film, then pitting corrosion could occur. And if pitting corrosion occur, this could go very fast and very aggressive. So erosion corrosion is usually a type of damage that happens because the motion of the electrolyte and the interaction with mechanical force and electrochemical corrosion. In places like vents or valves, so this valve where it basically creates tons of turbulence and cavitation after the valve is usually where corrosion could be observed, or at the bends when you have a bend or U-turn or use in the design, there is some locations where erosion could take place. As I said, stress corrosion cracking is another type of corrosion, but stress corrosion cracking, you need to have a stress, you need to have a specific environment, and you need to have a susceptible alloy. Otherwise, stress corrosion cracking cannot occur. And there's a typical failure of stress corrosion cracking. There was basically stress because of methanol there. So the methanol inside of this guy make it brittle, this steel, and then with the stress, as you see, this is the seam. The well, when they made the pipeline, they seam the pipeline on top. So this is where the stress is accumulated. The tensile stress is what basically is making the pipeline to stay like as a pipeline, and is making this very stress at that location. The environment basically is methanol, which makes the alloy susceptible to crack. And that's what exactly happened then in the stress corrosion cracking. When it cracks, it could happen due to different scenarios. For example, it should have certain temperature to make it susceptible. For example, carbon steel, to make it susceptible carbon steel to failure, needs to have at certain temperature, needs to have certain pH. That's very important, usually near neutral pH. It should have certain value of cathodic protection, which is usually minus 700 millivolts versus the silver chloride. It should have some, of course, it should have the stresses, it should have probably some cycling, and must have, it could be a very old segment that also is susceptible to make it susceptible, and it should be very close to some sort of vibration source. It could be intergranular or transgranular. And it depends about material, and it depends also about the stresses on this. So this is very important, but it's, as I said, it's as a result of this triangle there and the interaction of this triangle of stress corrosion cracking. And finally, I will talk about MIC, microbial induced corrosion. Microbial-induced corrosion is the degradation of metal caused by activity of organisms, usually bacteria. Usually bacteria that eat the sulfate on the oil, like SO4 minus, the sulfate elements on the oil, and as part of the metabolism of this eating the surface, all the waste of the bacteria is very acidic. They produce acetic acid or nitric acid, and it could go very low in pH, damaging the steel surface. The mechanism is basically the production of metabolites. Bacteria may produce organic acids, inorganic acids, sulfides, and ammonia. Destruction of protective layers. So if we have iron sulfide or iron carbonate or even coatings, it could be damaged by bacterial activity. The hydrogen embrittlement by acting as a source of hydrogen and or through the production of hydrogen sulfide. Bacteria can cause that damage. Formation of concentration cells at the metal surface, and in particular oxygen concentration cells. Modification of corrosion inhibitors. That's exactly how the bacteria produce. So let me go back to the stress corrosion cracking thing. When we have in the surface this crack is propagating as the stresses are accumulated along the pipeline. So the stresses are because hydrogen penetrates into the microstructure and then expand as hydrogen plus expand to hydrogen 2 and then make the stresses there, and it's basically growing and penetrating in that. With this type of corrosion, I will ask you to read the section in your books, chapter 3, that talks about types of corrosion mechanisms. But with your document that you send with your failure, then you are basically set, and you understood now the types of corrosion and the ways to mitigate these types of corrosion.